Hello guys, welcome back to Maison African Motives. Still working on our condensers on the power machines N5. We've got the question paper that is of November 2019 that we're gonna consider. Question 4.1, that's question 4, which is 4.1, whereby we are given a condenser. It receives 8,500 kilograms steam per hour. So we've got the mass of steam in this case with a dryness fraction of 0.8. So we are given the mass of steam, 8,500 kilograms per hour at a dryness fraction of 0.85, which is our dryness fraction, 0.85. The barometer reading and manometer reading is, so we've got the barometer reading, which is 760. Then we also have the manometer reading, which is 660. So given the manometer reading 660 millimeters high in this case. And also we have got the mass of air is, so this time we are given direct the mass of air. Remember, there are some conditions where you have to calculate the mass of air from the mass of steam. Here we have got the mass of air direct. So the mass of air in this case being 0.25. All right, so given 0.25 kilogram per second, this is given as 0.25 kilogram per second, whilst air pump and the condensate temperature is, so we've got the temperature of the condensate air pump at the same time, which is at 45.8 degrees Celsius. All right, that's it. Then the cooling water enters at 20 degrees Celsius and leaves at 38. So given the inlet and the outlet temperature, which you can just even write as T1 and T2. So the inlet temperature, T1, that's 20 degrees Celsius, and the T2, which is the outlet temperature, which is 32 degrees Celsius in this case. All right. Then the gas constant, which is 0.3 kilojoule per kg Kelvin. That's per kg degrees Celsius. We're going to use this in degrees Celsius, all right, for this value. All right, no problem. It's going to depend with the formula that we're going to use. If it is for pressure, if we're going to use the pressure for PV, maybe, or here we're going to use the capacity. So it's fine that we just leave it like that in kilojoule per kg Kelvin. Okay. Then the capacity, the specific heat capacity of water. So we've got the specific heat capacity. This one is for water, 4.187 kilojoule per kg degrees Celsius. All right, so we're gonna have this one for water in this case. Okay, that's it. Okay, 4.11, calculate the absolute pressure of steam in the condenser. So we need the absolute pressure. So remember, the absolute pressure can be taken from the barometer and manometer readings in this case. So working with a condenser from our formula, we are given this formula from our formula sheet for the absolute pressure, but you just need what to do on the formula. If you're dealing with a condenser, you're going to subtract on this formula for pressure is equal to the barometer reading minus the manometer reading or the vacuum reading times 101.325 over 760. All right, so that's we're going to have our pressure, which is the absolute pressure in a kilopascal. All right, the barometer reading, that's 760. In this case, this one is 760 minus the manometer or the vacuum reading, which is 660. So that's 660 multiplied to 101.325 over 760. All right, so this is going to give us the absolute pressure in this case. So our absolute pressure is going to be given as 13.3332. That's going to be a 2 in this case in a kilopascal. All right, so it's going to depend with where are we going to use this pressure. If we are to use this pressure to find the enthalpy, we are going to need this pressure to the nearest whole number. So it's just going to approximate this to the nearest whole number, which is going to be 13 kilopascal. This 3 cannot change this, so it's going to be 13 kilopascal. That is if we are to use it for any part that needs us to use the steam table. But if we are to use this pressure for any other calculations without where the steam table is not even involved, we're just going to use this pressure as it is in to 3 decimal places, as it is like this. All right, so that was our absolute pressure, 2 marks for that. 4.12, the mass of cooling water in kilogram per hour. Take note, we are given in kilogram per hour. That is the mass of cooling water. Remember, I talked about the heat that can be emitted and the heat that can be absorbed by water. That's where we can calculate the mass. That formula can give us the change in temperature. It can give us the T2, which is the output, or it can be, they can ask you to calculate the inlet. You can use that formula to manipulate whatever that you are to calculate. So here we can focus on that formula here because of the information that we have. So we can think of that to say the heat to be emitted in this case, all right, to the heat to be emitted by steam, that's the heat emitted by steam is going to be equal to the heat that is going to be absorbed by water in this case. All right, so you're going to calculate the heat from steam, which is the enthalpy that you're going to have from the steam, which is going to be the mass of steam into H wet minus HC at the condensate. All right, like I said, there's another formula for HS plus HC that you can use. But this is one of the best. So I'm going to focus on this formula until we understand it. After that, I'm going to bring you another formula so that you do not miss any part. That's why I keep on repeating similar questions so that we understand this formula. All right. Then for the heat absorbed by water is going to be mass of water, the specific heat capacity of water times the change in temperature for water, which is T2 minus T1. So there we've got T2 and T1. So we're going to extend our formula. Let us extend our formula. So here we're going to have mass of steam into H wet. Remember, H wet is given from HF, HF plus X, the dryness fraction, times HFG for the evaporation. So this whole part here represents our H wet. Then we're going to subtract HC, which is from the temperature at the condensate. All right, so that's it. We're going to have the mass of water, the specific heat capacity of water, the change in temperature, that's T2 minus T1. So here we're going to use this because we've got T2 and T1. We are not given directly the change in temperature, so we have to substitute our values properly. So that's it. That's it. So this HF and HFG, like I said, guys, they are taken, the value of HF and HG, they are taken at the absolute pressure, P. So they are taken at P, which is our absolute pressure in this case, at the absolute pressure. At the absolute pressure, we obtained our absolute pressure here. So that's where we're going to use the whole number, this one, because on our steam table, we do not have decimal. So that is at 13 kilopascal. We need the value of HF and the value of HFG. Then HC is the value of HF. This is HF at TC, which is the temperature of the condensate. In this case, TC, we've got the temperature here of the condensate that is at 45.8 degrees Celsius. So that's at 45.8 degrees Celsius. We're going to find the value of HF there. So that's it. Just going to substitute our values. Then we calculate the mass. We find the mass of water. So since the mass of steam, let's substitute the mass of steam here is in all right, the mass of steam. Do we have the mass of steam? We wrote it somewhere here. The mass of steam is in kilograms per hour, but here, all right, they need also in kilograms per hour. So there's no conversion that we're going to do. We are not going to convert anything because already the mass of steam is in kilogram per hour. So that means also the mass of cooling water is going to be in kilogram per hour. So the mass of steam, let us substitute the mass of steam here, 8,500. This value here for the mass of steam, 8,500. So here, just going to substitute our values. So that's 8,500 into HF, which is at the pressure of 13 kilopascal. So we're going to need HF and HFG at 13 kilopascal. So let's consider pressure. Under pressure here, we're going to need HF and HFG at 13 kilopascal. So pressure here of 13 kilopascal, it corresponds, so these are the values here. At HF, that's HF under this column. So this is the column for HF. This is the column for HFG. All right, so under the column of HF here, we've got 214. Then HFG, we've got 2,380. So that's 214 for HF. So you're going to substitute here for HF, which is 214 plus X, our dryness fraction. Take note our dryness fraction here, X is 0.85. So that's going to be the product of 0.85 times HFG, which is for evaporation. At the same pressure of 13 kilopascal, we obtained HFG here as 2,380. So it's going to be 2,380 minus HC. So like I said, HC is the HF, is the value of HF at TC. That's at 45.8 degrees Celsius. So at 45.8 degrees Celsius, we need the temperature this time. So we are under the temperature, under the saturation temperature here. 45, we need the value of HF there under this temperature of 45.8. So at 45.8, this is the temperature here. This is gonna be the value of HF. So the value of HF here is 192. So we are going to use 192, the value of HF. All right, so that's it. So as you can see, this one is a direct and straightforward substitution. That's why I'm saying let us try by all means to know this formula. Yes, I'm gonna bring you another formula where you are adding your values. Here you subtract H weight minus HC. So take note, H weight minus HC. Yes, direct, we know guys, the heat absorbed by water, specific heat capacity of water times the change in temperature. So that's it. We do not have the mass of water here, but we've got the specific heat capacity of water. Given the specific heat capacity of water is 4,187. So that's 4,187 times the change in temperature T2 minus T1. So that's our T2, 38 minus 20. So you're going to have 38 minus 20 in this case. All right, so that's it. You're going to obtain the mass of water from here. So it's either you're going to combine this and also combine this, then you divide, or you can just divide at once. If you divide this side by, okay, that's a negative there, by 4,187 into 38 minus 20, both sides, you're going to divide also this side here by this part, which is 4,817. So it's going to be 4,817 into 38 minus 20. Okay, so that's it. This will cancel, and also this bracket will cancel. We remain with the mass of water in this case. All right, so if we are to simplify properly this value here for the mass of water from this side here, if we simplify everything from that side, we are going to obtain the mass of water as 230,000. So that's 230,641,1379, which is 138. So it's going to be 138 in kilograms per hour. So like, because the mass here for steam, it was kilograms per hour. So it means also the mass of water, you are going to obtain it in kilograms per hour. So that's the formula. The heat emitted by steam to the heat that is absorbed by water. guys, you can play around this. In another formula, it's gonna be here, it will be HS plus HC. So I shall talk about that formula which uses HS plus HC. I'll just have it as a separate class so that I do not confuse you. For now, let's stick to this one. If you are watching this for the first time with us, unless you have been doing this topic and you have been taught another way, you can use that way that you've been taught. But if you are having our classes here using my YouTube channel, stick to this one for the meantime until I bring you another new formula so that you can compare, so that you do not have confusion. Then we've got the question of the capacity of air in this case. All right, sometimes they just do ask this question and the capacity, or they ask this question and the mass, but here they have both. So do not confuse between when you are asked to calculate the capacity of air, which is the volume of air. This is cubic meters per minute. We shall talk about that, but the capacity, you're talking about the volume of air. For that one, you go back to the application of gases, which is thermodynamics of gases, from your PV formula. We are going to see that. All right, I'm just going to remove this. I don't think you're going to need it. So from our PV formula, we know that PV is equal to MRT. All right, so we understand. So that's 4.13. PV is equal to MRT. So it means to obtain the volume of air, we must have the pressure of air, the mass of air, and the temperature of air. So that means the volume of air is going to be mass of air over PA. So we need to determine a lot of things on this part, which is actually not too much, but we just have to calculate this. One, we're gonna need the mass of air, which this time we are given direct. Sometimes they give you, I talked about this, that they give you from a ratio where you calculate the volume of air from the air leakage. If you are given air leakage ratio, you're gonna use the air leakage ratio times the volume of steam times the volume of steam. But in this case, we are given direct the volume of air, so we're not going to consider multiplying anything. We have this volume of air here. I mean the mass of air, not the volume. Sorry for that, guys. The mass of. So it's going to be ratio times mass of what? Mass of steam. So, but here we are given. So TA is from our suction point. We are given temperature and air and suction at the same point, which is 55, 45,8 degrees Celsius. So that's going to give us our TA in Kelvin. Supposed to have this R in Kelvin, per Kelvin. So that will be 45,8 plus 273 in Kelvin. So that means we're going to obtain our TA, which will be 318,8 Kelvin. All right. So we now have TA. Then PA is the pressure that we are going to have for air in this case. So we're going to have the pressure for air. Where are we going to have this? We're going to take it from the total pressure and the suction pressure at suction. So you've got the air pressure plus the pressure at the suction point, meaning the condensate in this case. So this PT is the total pressure that we obtained from our calculation here of this absolute pressure. That's our PT in this case, the absolute pressure. So like I said, this 13 kilopascal was for our calculation because for those steam table calculation, that's where we're to use this P as 13 kilopascal. But for a normal calculation like this one, we do not have any steam calculation to be involved. You can use the actual value that we obtained before we estimated, we approximated to the nearest number. Our pressure was 13.332. So you can use that part as, so that's our total pressure, 13.322. So we've got 13.332 is equal to the pressure of air plus the pressure at the suction point, which is at the condensate, taken at the condensate temperature of 45 degrees Celsius. So at this temperature here, what is going to be the pressure? So you're gonna need our steam table at 45,8. So that's at 45,8. We're gonna need this, sorry for that, at 45,8. The temperature is 45. So we need temperature under temperature. In this case, we're gonna need the value of pressure under temperature here. We need the pressure at 45,8. So 45,8, we talked about this before. 45,8 is here. The corresponding pressure there is 10 kilopascal. Remember, our pressure measured in kilopascal. So that's we're going to have our pressure there as 10 kilopascal. So that's the pressure at the suction point. So you can calculate PA from there, which is the pressure of air. Subtract this 13.332 minus 10 is equal to PA. So that's the pressure is going to be 3,332 kilopascal. All right, so that's it. I think we've got everything now. We calculated this. So that will give us the volume. But this volume, as we can see, if we are to substitute here, we are going to see that because of the mass here, which is in kilogram per second, we are going to obtain our volume in kilogram per, we are going to have our volume in cubic meters per second, because this is per second. So what can we do to obtain this in kilogram per minute? We can change that mass to kilograms per minute. All right. So let us just convert at once, because we just want to convert, we just want to insert our values at once. So this one is fine in Kelvin, in kilopascal, but this one is not going to give us the volume in cubic meters per minute. It's going to give us our volume in cubic meters per second. Yes, you can convert on the final answer, or you can just convert the mass direct. We are given the mass of air as 0.25 kilogram per second, means 1 second. So this is same as per minute. If we convert this to a minute, it's going to be 0.25 over, okay, kilograms over 1 second to minute is 1/60, which is in minutes, or you just multiply by 60. 0.25 times 60. Remember, 1 minute is equal to 60 seconds. So 1 second is going to be equal to what? That is the question. 1 second is going to be equal to what? So it's going to be 1/60 times 1 minute. So that's 1/60 times a minute. So in a second, we've got 1/60 minutes. All right. So that's it. We're going to have the mass of air, which is 0.25 divided by 1/60, or 0.25 times 60. We are going to obtain 15 kilogram per minute. It's now per minute. So if we use this mass here in kilogram per minute, it means we are going to obtain our volume in cubic meters per minute. So that's it. That's what I'm trying to say there. So we're going to just substitute. So the volume of air is going to be the mass of air, 15 kilograms per minute, times R, in this case 0.3, times the temperature of air in kelvins, which is 318.8, over the pressure of air, which is the pressure of air, which is 3,332 kilopascal. So that's it. That's it. We are going to obtain our volume of air, and as I said, it's going to be in cubic meters per minute, since we used the mass in kilograms per minute. So also our volume is going to have per minute. So the volume of air at the end was going to be 430,5522, which is 552 in cubic meters per minute. So that is the volume of air, the capacity of air. If the question is asking you on the capacity, you use the formula PV, which is PV is equal to MRT. If the question is on the mass of water, or maybe the temperature at the output, or the temperature at the inlet, you use the formula for the heat emitted by steam to be equal to the heat absorbed by water. These are the two major questions that you'll be given on condensers. It's either, like I said, they are going to separate, they'll ask you these two questions on one question, or they're going to ask you this one, or they will just ask you this question direct as it is, but you must know that you must first find absolute pressure in order for you to have this. The same thing, in order for you to have the capacity of air, which is the volume of air, you need to have absolute pressure. So that is how they can separate a question on condensers. If they want to ask you about the cooling, the mass of cooling water only, or they want to ask you about the capacity of air on each one on itself. But these are the questions that you are supposed to expect whenever you are dealing with a condenser. So also make sure you watch the videos on the calorimeters so that you check the difference on the pressure concept. All right, on the calorimeter, we are going to find our pressure being added. On the condenser, we are going to subtract, because in the formula sheet, you're just going to be given the formula as P is equal to Bm plus or minus mm, which is for the manometer reading, times 101.325 over 760. So you are supposed to know the addition there. You are going to use it on a calorimeter. All right. Then the subtraction that we have on this part, we are going to use it when we are dealing with a condenser. When dealing with a condenser. So that is what you're going to have. And on the condenser, it's the heat emitted by steam to the heat absorbed by water. When you're talking about a calorimeter, we're going to be talking about the enthalpy before throttling and the enthalpy after throttling, whereby we're talking about the heat, the wet steam that is being changed to either a dry steam or a superheated steam. That's a calorimeter concept. So check the difference between the condenser and a calorimeter. Those are the two questions that they might ask, and sometimes they might combine a question of a calorimeter and a condenser at the same time, or they just ask them separately, or in another question paper is just a condenser. So you need to know the difference so that you'll be able to attempt these typical questions in the final exams.